Piecewise functions. When finding a piecewise function rule for a graph, the graph of the function is usually shown, such as this one here to the left. The graph is composed of a sloped segment connecting two horizontal lines. How might you write a formula or a rule to describe the graph? Take a moment to pause this video and think about it, and when you're done, unpause it. With piecewise functions, the task of finding a formula is actually three problems in one. The right to the left has a formula, the segment in the middle has another formula, as does the ray shown to the right. Let's build a rule to describe the graph. When working with piecewise functions, we are finding formulas for the function piece by piece. And then we also have to identify domain restrictions for each piece. Let's start with piece number 1. We can see that this function from -2 all the way to -infinity, or for x values less than or equal to -2, the function has a value of -3. So we can write this as f of x is equal to -3 if x is less than or equal to -2. Now let's look at the second piece. We have a linear function that has a slope of 2, because we're rising 2 and running 1 each time, and its y-intercept is +1. So f of x is equal to 2x plus 1 for x values between -2 and +1, not including the -2, because that was included in piece 1. Now let's look at piece number 3. In piece number 3, we again have a horizontal line. Its function value is 3 for x values greater than +1. And again, we have this as greater than 1 because being equal to 1 was taken care of in piece number 2. We then write the three formulas, one for each piece, and identify the domain restrictions for each one. And we put it all together in one package as shown below. We have that f of x is equal to a big, huge curly bracket. If you're doing it by hand, you can think of it as an arc, a little spike, and another arc below. And then we have -3 for the first part if x is less than or equal to -2. We have 2x plus 1 if x is between -2 and +1, not including -2. And we have that it is equal to 3 if x is greater than 1. When writing the piecewise functions, you could use the word if in between the function values and the conditions. You could also use the word for instead of if, and sometimes commas are also used for this reason. As we have found, a piecewise function is a function that contains at least two equations or pieces, where each equation or piece is defined in different parts of the domain. In our example, we have a piecewise function that contains 3 equations or pieces. Here's another example. We're going to write a piecewise rule to model the piecewise function shown in the graph to the left. So let's begin with this first piece. It is for x values that are less than, notice there is an open circle here, so there is no equal to, and the x coordinate boundary is 0, and the y coordinates or the function coordinates are -1. Now our second piece is from 0 to 2, and both endpoints are closed. So we have the equal to sign showing in the inequalities. And within this section of our domain, the function value is 2. Now for the last part, for x values greater than or equal to 3, our function has been assigned to be -3. Notice that there is a gap between this +2 and +3 that is definitely permitted with piecewise functions. So as long as you include the correct inequality symbol for the domain restrictions, you should be okay. And here's the solution for the piecewise rule that models this function. It's -1 if x is less than 0. It is +2 for x values between 0 and 2, including both endpoints. And it's -3 if x is greater than or equal to 3. There are times when modeling a function with 2 or more rules is a requirement. And here's an example of a parking fee schedule that could be used for a parking lot or a parking garage. First rule is that they charge a minimum of $10 for the first 5 hours. So from time being 0 to time being 5, you're at $10. Rule number 2 is they're adding $2 for each additional hour. So if you're there for between 5 and 6 hours, you're going to pay $12. So that's 10 plus 2 more. If you're there for between 6 and 7 hours, you would pay the $10 plus 2 additional sets of $2, so that would be $14. They have a final rule that the maximum number of dollars that you would pay in one day is $26. So the graph that is shown here is modeling this rule. So it starts at 10 all the way up to 5. So at this point right here, it's going to be an open circle, and then it'll be closed up here and open, and then closed and then open, closed and then open. So the graph will look like this if you include all the open and closed circles. And this piecewise function is an example of the greatest integer function. It's sometimes called the step function since it looks like a set of stairs as you move from left to right. You input a real number and its output is the greatest integer that is less than or equal to x. And here are some examples. The greatest integer of 2 is 2. The greatest integer of 4 and 99 hundredths would be 4. The greatest integer of -2 and 1/10 is going to be -3. Now let's discuss how to evaluate piecewise functions. To evaluate a piecewise defined function f, at a point x equals a, we are looking for the value f of a. Since a piecewise function has more than one rule, we need to be careful to pick the rule that applies to a particular argument, x being equal to a. So here's our example piecewise function. F of x is equal to the absolute value of x minus 2 if x is smaller than 1. The function is equal to x squared plus 3 if x is greater than or equal to 1. So let's evaluate these 4 problems. We have f of -3. Well, -3 is less than 1, so we're going to substitute it into the first piece of our piecewise function. So we have -3 minus 2 inside of the absolute value. So that's going to be the absolute value of -5, which is equal to 5. Now if we find the function value at 5, well, 5 is greater than 1, so it fulfills the second condition. So we're going to substitute it into our second piece. So we have 5 squared plus 3, which is equal to 25 plus 3, which is equal to 28. Now if we look at our third piece, we're finding the function value at 1. Well, wait, 1 is included in both of these conditions. But the question is, where is x equal to 1? It's in the second condition. So we're going to substitute 1 in for x in our second condition, so that's 1 squared plus 3. So that's going to be 1 plus 3, which is 4. And now our last problem that we have here, f of -10. -10 is smaller than 1, so we're going to substitute it into our absolute value. So we have -10 minus 2, so that's going to be the absolute value of -12, which is equal to 12. And here we can see the solutions to the example that we found, and all the solutions that were calculated match what appears on this slide. Here's another example for evaluating piecewise functions. To evaluate a piecewise defined function h at x equals a, we are looking for the value of h of a. Since a piecewise function has more than one rule, we need to be careful to pick the rule that applies to a particular argument for each a value. We have that h of x is equal to the absolute value of the quantity x plus 1 if x is a rational number. H of x is equal to x squared plus 1 if x is irrational. So let's evaluate the function at these four x values. So first we have h of -3. Well, -3 is a rational number. So that's going to be the absolute value of -3 plus 1, which is going to be the absolute value of -2, which is 2. Our next problem that we have is h of pi. Pi is considered to be irrational, so we're going to substitute it into the bottom piece. So that's going to be pi squared plus 1. You can leave your answer in this exact format. You don't have to fully evaluate it in a calculator, but you could if you would like to. Now let's look at the next one. We have h of the square root of 2. Well, square root of 2 is irrational, so we're going to do the square root of 2 squared plus 1. That's going to be 2 plus 1, which is equal to 3. And finally, we have h of 18. 18 is a rational number, so we're going to substitute it into the first one again. So we have the absolute value of 18 plus 1, which is the absolute value of 19, which is equal to 19. And here are the solutions to these four example problems, and they do match the solutions that we found. The graph shown below is a piecewise defined function. Here's its rule. P of t is equal to 10 if the time values are between 0 and 5, not including both endpoints. P of t is equal to 12 plus 2 times the greatest integer of the quantity t minus 5 for t values between 5 and 12, including 5 only. And P of t is equal to 26 for t values between 12 and 24, including both endpoints, where P is the parking fee and T is the time in hours. We're going to evaluate this function, P of T, at 3.5, 9 1/10, and 20. First, let's look at the parking fee for 3.5 hours. So if we read our graph at 3.5 hours, it's just going to be at 10. We could also see that 3.5 falls between 0 and 5, so its output is going to be 10. Now we have to find the parking fee for 9 1/10 hours. If we read the graph at 9 1/10 hours, that'll be a little past 9, and that will end up being at $20. We could also substitute 9.1 in for t here. 9.1 minus 5 is 4.1, and the greatest integer of 4.1 is 4. 4 times 2 is 8, and then 12 plus 8 gives us 20. Now let's look at part C. We're finding P of 20. So if we go to 20 for our x and we go up to our function, it's going to be that $26 because it's any time where the time value is between 12 and 24, including both endpoints. And here we can see the solutions to evaluating this piecewise function, and the solutions found do match the solutions that we came up with. Here's another example. We're going to let C be the cost in dollars of shipping a package on Staten Island based on the weight in kilograms. We have that the shipping cost would be $8 if the weight falls between 0 and 4 kilograms, not including both endpoints. The cost would end up being $12 plus 4 times the greatest integer of the quantity x minus 4 for weight values between 4 and 10, including only the lowest endpoint of 4. And then the cost would be $35 for any x value that is greater than or equal to 10 kilograms. So let's evaluate our cost for each of these weights. We'll begin with 2 7/10 kilograms. Well, 2 7/10 kilograms falls between 0 and 4, so the final cost will be $8. We can also go to 2.7 on the graph, and we can clearly see that it falls in the $8 mark. Now let's look at part B, the cost for shipping a package that is 6 4/10 kilograms. Well, that's going to fall between the 4 and 10. So we can substitute 6.4 in for x. We would get 6.4 minus 4, which is 2 4/10. The greatest integer of 2 4/10 will be 2. 2 times 4 is 8. 8 plus 12 is going to be 20. We could also go to 6 4/10, that's right about here, and it does directly fall or come out as $20. Now let's look at the cost for 12 3/10 kilograms. So 12 3/10, that's going to be right about here. It looks like it's going to be at that $35 mark, and it is because 12 3/10 is greater than or equal to 10. So the final cost will be $35. Here we can see that the solutions to this example problem match the solutions that were found. Next, let's discuss the translation of piecewise functions. We're going to let f be a piecewise function displayed in red in the coordinate plane below. Two of its translations are shown, g and h. Write the new rule or formula for g and h, then determine the domain and range for each. So we'll begin by shifting f down 4 units to get g. Notice we go 1, 2, 3, 4 down for all points, 1, 2, 3, 4. Therefore, g of x will be f of x minus 4. And now the domain for g of x will end up being from -4 to -2. -4 is included, but -2 is not, in union with 0 to +2, where +2 is included. The range will end up being from -6 to -4, including -6, and then in union with -3 to -1. It's important to note that the domain for both f and g are the same. However, the range is the section that is impacted by this translation because it went down 4 units. Now let's look at h. We're going to shift f to the right 3 units to get our function h. Notice we can see 1, 2, 3, 1, 2, 3. So therefore, our h of x function is going to be f of, and then in parentheses, x minus 3. The domain for h is going to be from -1 to +1, where -1 is included, but +1 is not, in union with 3 to +5, where +5 is included, but +3 is not. So in bracket notation, it's going to look something like this. Now let's talk about the range. The range for our function h is going to be from -2, including -2, to 0, but not including 0, in union with 1, including 1, to 3, not including 3. So h of x is included in -2 to 0, -2 is a bracket, 0 is parenthesis, in union with bracket at 1, open parenthesis at 3. It's important to note that the domain will change for the horizontal translations, as we see, but the range would remain the same, like the range for f is the same as the range for h. Similarly, the range will change for vertical translations, as noted when we found the domain and range for g. The domain stayed the same as what the domain was for f, but the range was impacted. Here's an example of a translation of restricted functions. We're going to let f of x be equal to x squared for x values between -1 and +2, including both endpoints, and only those x values. we're going to write the rule or formula for the new function after the given translation. So the first one that we're going to do is we are going to shift our function f to the right 3 units. And when we do that, 1, 2, 3, we're going to end up with g of x. And g of x is equal to f of x minus 3 because we shifted it to the right 3. So if we take x minus 3 and substitute it in for our x value in our function, that will make it become x minus 3 quantity squared. And this is true for x values within the closed domain from positive 2 to positive 5. Now let's look at h. We are going to shift f down 4 units, and that does indeed give us h. So h of x is equal to f of x minus 4 because we're shifting down 4 units. So then if we take f of x and substitute it in this place, we'll end up getting x squared minus 4. And then this is valid for x values contained in the closed interval from -1 to positive 2. And here are the solutions to this example problem, and they do match the solutions that we found. We found that g of x was equal to the quantity x minus 3 raised to the second power for x values between 2 and 5, including both endpoints. We also found that after shifting f down 4 units, we end up with h of x, which is f of x minus 4, or x squared minus 4, for x values contained in the closed interval from -1 to 2. It's worth noting again that the domain will change for horizontal translations. We can see that that happened here. But the domain will not change for vertical translations. So the domain from f and to h will be the same from -1 to 2. And this is occurring because the domain of f of x minus h can be set up as an inequality. Like you can take x minus h and substitute it in for x in the original domain. And then if you add h to both sides of each inequality, you will end up having -1 plus h is less than or equal to x, which is less than or equal to 2 plus h. And that indeed is the domain of our new function after this horizontal translation. If we take -1 and we add 3 to it, you get positive 2. If you take 2 and add 3 to it, you do get positive 5.